Our next speaker is Dr. Karyn Rogers. Karyn joined RPI in 2013. She is an associate professor in Earth and Environmental Sciences, the director of the Rensselaer Astrobiology Research and Education Center, and co-chair of the National Academy of Sciences Committee on Astrobiology and Planetary Science. Karyn's talk today is entitled Searching for Life and Its Origins, an astrobiologist's journey through the solar system. This will highlight her research, delving into the boundaries of life, investigating early Earth environments that could have fostered or hindered the emergence of life, and pioneering new methods to detect potential signs of life within the solar system. Karyn, please join me on stage.
Uh-oh, that thing has happened. I have lost the mouse. Got it, there it is, it's back, thank you. Excellent, that's perfect. Yes, okay, it's a Polytechnic. We know how to run slides here, it's fantastic. Thank you, Rebecca, for the introduction, and thank you all for coming. As you know from the introduction, I have a lot to cover in 12 minutes, but before I start with life's origins, I have something even more important that I want to talk to you about, and that is a thanks to all of you. I arrived at RPI 11 years ago, and I knew it was a great school, but I didn't really understand at the time how truly spectacular and unique and special it was. I have been astounded over my more than a decade here. RPI has come to be my home, and all of you have come to be my family. The special piece of RPI is an aura of excellence, of innovation, of taking risks, of entrepreneurship. It really inspires all of us here, staff and students and faculty, scientists and engineers and musicians and economists and architects. We all get inspired by reaching for something that we've never even imagined before. That oozes out of the walls here. And it oozes out of the walls because of all of you. I know it's because of all of you, because that's what you gave to this place. And so I want to thank you for giving me this opportunity, this gift that is RPI. And thank you all for that. And here at your homecoming, I want to say welcome home. And I also want to, speaking of home, give you this other perspective on your home, the Earth, right? From this perspective, humans can't help but ask some questions like, how did life start? Are we alone? Where should we look for life elsewhere in the universe? And I thought to myself, these are interesting questions. I'll see if I can't make a career out of that. Here I am, still lots to do. If that's your set of questions, there's an approach that you might take. You probably start with picking your favorite planet or moon. And the first question you might ask is it habitable? The picture on your middle right is what Mars likely looked like early in its history, with a shallow ocean covering the northern hemisphere. And so you might ask, was there ever life here? And thus is launched the Mars exploration program, with numerous orbiters, landers, and rovers exploring the planet for signs of life. In another, you might look at a place like Europa, a moon of Jupiter, where there are hydrothermal systems expected at the bottom of the ocean. That's the picture on your bottom right. And there you might ask, well, there's life in our own hydrothermal systems. Is there life there, and can it survive? And I'll get to that question in a minute. But if you start with this planet, what you might ask is, how the heck did we get here? We are a good example that life can survive on this planet, but how did it start? And that's where I want to start this talk. And so, origins of life and how sort of the prebiotic chemistry that led to life's origins on this planet is not something new, and this is traditionally how it's been done. You start with life as we know it. You break life as we know it up into its little tiny bits, and you pick your favorite bit, your favorite molecule, and you try and go build that molecule in the lab, and then you do it. And then you run down the hallway and knock on a door like mine. And you say, hey, you understand the planet. Here's my beaker. Where can I find this on the early Earth? And I say, oh, I'm so sorry, but nowhere. It's tragic, I know. You just think you found life's origins, but not on this planet, and so you are lost. And so this is sort of the approach that has been taken for a while, and we decided here at RPI to turn this on its head. So what did we do? We started with the Earth, and we said, hey, what does the early Earth look like? I'm gonna build all of that in the lab, and then I'm gonna see if I can't get life out of that, if I can't get all of life's bits made. And so our fundamental question in the Astrobiology Center is how and where did life originate on Earth? Tiny little thing. I'm sure I can vacation in a couple of months because we'll all be done and we'll have to move on to something else. If this is your question, you have to start out with what did Earth look like? I am really grateful that I've been able to work with a scientific illustrator who took the ideas in sort of my head, which are very jumbled, and I have to say I'm not an artist, and she turned them into these pictures. And the early Earth is a little different than what we know of it today. The ocean was probably full of iron. The sky was probably orange. I know you couldn't breathe at all. There was lots of impactors. There were lots of hydrothermal systems, both on the surface and at the bottom of our oceans. And if we're going to understand life's origins here, we have to be able to move these environments into the lab. And so just across the way in the Science Center, in our basement, we are building all of these systems in the Early Earth Laboratory. We have a bunch of high temperature and high pressure devices. They allow us to mimic hydrothermal systems, black smokers, ponds on the surface of the Earth, at the edge of the ocean, in these weird environments full of methane and carbon dioxide and carbon monoxide. We can do all of that in the lab. And we have been building this out over the years, and we're really excited. In probably another month or two, we're gonna have a grand opening, so you should all come back. The hotels will be much more available then, so I invite you all back. So I wanna tell you quickly just a few vignettes of some of the work we do in this laboratory as part of the Astrobiology Center. I can't get to all of them, obviously, but here are some really interesting ones, I think. So back early in Earth's history, this planet was bombarded by meteorites constantly. You would think that would be really bad for life, but it turns out that these meteorites contain some of the molecules that we need for life to start. And so we had this great idea. I wonder if those molecules could survive. Because when a meteorite hits this planet, it makes a hydrothermal system. A hydrothermal system that has been modeled to look like this. Water flows through this system, moving all the stuff in that meteorite along these interesting flow paths. And what did I do? I got together with my student. I said, let's build it. Let's build that flow path in the lab. And so we built this thing, high temperature, high pressure, flowing through rocks. Do the organic compounds that might lead to life, do they survive? Do they get transformed? Do they polymerize? Do we end up with an elephant on the other side, right? So that's one question. It's 16th inch tubing, and so no elephants have come out yet. I don't know why. Thinking of something even more basic, if we can't get all of those compounds that lead to life delivered to us from meteorites, how might they be formed on this planet? And so in this other sort of tricky and interesting project, we're trying to make the amino acids and the proteins that are the reason all of you are here today. None of your cells do anything without proteins, right? We're trying to see how to make those without the help of life. You get your proteins probably by eating the breakfast you just had. But before there was life to make proteins, planets and moons had to do it entirely on their own in this abiotic setting. And so we're trying to figure that out. And we're doing it not just for our planet, But we're also looking at hydrothermal systems on Europa, which is a moon of Jupiter, hydrothermal systems on Enceladus, which is a moon of Saturn. And we're taking these very basic building blocks, CO2, N2, ammonia, these tiny little molecules, and we're seeing if we can't synthesize those in these hydrothermal systems that we're replicating in our lab. And so that's sort of number two. We've done this with lots and lots of different biomolecules. Amino acids are one, nucleic acids are another. We're about to get into the fatty acids. I think it's because as I get older, I get hungrier all the time, and so that seemed like a good idea. And then the final story I want to tell you about is searching for life elsewhere. And that is life in hydrothermal systems. And so we know that life exists on hydrothermal systems at the bottom of our oceans. I've been there. It's really, really fun. It's scary and exciting and oh my goodness. So I've been to the bottom of the ocean, lots and lots of life there, but there are hydrothermal systems on the bottom of Europa's ocean. And NASA is absolutely going to send missions to go see if we can identify life there. And so one of the questions we asked in the lab is, if we take a sample from the bottom of Europa's ocean, will we be able to identify life? And so imagine this, here's a hydrothermal system at the bottom of an ocean. If you grabbed a bubble with life in it and you brought it to the top, that's what would happen. Your cell would burst, you'd lose the DNA, you would never see life. And man, that $20 billion from NASA is wasted. That's not a good thing to do. And so we asked NASA if we could go have sort of a trip to a fake Europa at the bottom of our own oceans. And right pre-pandemic, we went to the deepest hydrothermal system on the planet, which is the Mid-Cayman Rise. We took this lovely vehicle, Jason, out to the bottom of the ocean with our high-pressure sampler, and we asked, essentially, how is it that we can best sample life in this potential environment? And we were worried mostly about decompression, and here is why. This right here is a device that's been used for decades, growing microbes at pressure in the lab. The blue line on that graph is what happens to the microbe as you try and interrogate it and ask it questions. High pressure, low pressure, high pressure, low pressure, high pressure, low pressure, high pressure. Wow, that sounds terrible. And I thought, I wonder if they don't like that. And so we built a new device called the PUSH, the Pressurized Underwater Sample Handler, which has no change in pressure. And we asked the microbes, which one do you like better? Simple questions we ask in my lab. And so I will show you the results. And just as a preview, if cell numbers go down, that's death. If cell numbers go up, that's growth. Ha! You could have guessed, right? I mean, clearly, these wild changes in pressure are bad for life, and we end up with cell death. And when we use our PUSH, we prevent death. And so the PUSH prevents death. Now that I've done this, I'm going to work on taxes, but I think death was actually easier. So as I wrap up my talk, I want to show you how we got to this place, because it wasn't me. It was all of you, and it was all of these folks. These are students and staff. We have high school students and undergrads and graduate students and postdocs, and we have a Fulbright scholar in the lab right now. All of these people come together. They are pulled together at RPI to do this absolutely amazing, amazing work. And we couldn't be more grateful to be able to do it. And I know all of these people in 10 years are going to be sitting out there where you are, or perhaps even standing up here where I am. And that's because you have given us the institution that allows us to make this happen. So with that, I'd like to thank you.
Wow, wow, wow. Thank you, Karyn. Terrific.